Solving the Kepler problem using only Newton's laws, high school level math, and an intuitive approach to the concept of limits. Video 3. Proving Kepler's first law. Let's begin with a hypothetical ovoid orbit. Let's take a closer look at what is going on with our imaginary triangles as dt approaches 0. We want to develop a different way of computing their areas so that we can find a new way of expressing the value of our constant k. Let's construct a triangle by connecting the ends of r and r' with a line segment. The area of this triangle, of course, equals dA, which equals 1/2 times r times a, the altitude shown here. Let's rewrite the equation this way. A equals dA divided by the quantity 1/2 times r. And let's save this equation for later reference. The angle indicated here is the angle that we have decided earlier to call phi. And recall that the length of the short side of our triangle equals v times dt. You can see that a divided by v times dt equals the sine of 180 degrees minus phi. And therefore also equals the sine of phi. Rearranging, we find that a equals v times dt times sine phi. We now have another equation showing a second way of expressing a, so let's set the two equations equal to each other. We get v times dt times sine of phi equals dA divided by the quantity 1/2 times r. Solving for dA, we get dA equals 1/2 times r times v times dt times sine phi. Now we simply divide both sides by dt. And so with this equation, we have found a new way of expressing a value for our constant k. We want to explore this formula a little bit by considering the fact that sine phi changes throughout the orbit. However, there is at least one moment during the orbit when sine phi equals 1. When the planet is at a point where it reaches its closest approach to the Sun, we say it is at perihelion. It is logically necessary that the planet be at perihelion at least once during its orbit. We can position the orbit relative to our coordinate system so that perihelion occurs when the planet has an angular position of 0 degrees. Let Rp equal r at perihelion. And v0 equal the velocity vector at this moment. The angle phi must be 90 degrees based on the argument we made earlier. At perihelion, the planet is in a transition state from a prior time when r was getting smaller and phi was less than 90 degrees, and a future time when r is going to get larger and phi will be more than 90 degrees. The sine of 90 degrees is 1. So, dA dt equals 1/2 times Rp times v0. So, if we know the value of Rp and v0, we know the value of the constant k at any point along the planet's orbit. Now, k has an interesting relationship to the angular momentum of the planet. We haven't talked about angular momentum because Newton did not formally define it, and because there is no requirement to define it in order to prove Kepler's three laws. Nevertheless, it is a quantity analogous to linear momentum. Just as Newton's law of inertia corresponds to conservation of linear momentum, so too does proof of Kepler's second law correspond to establishing conservation of angular momentum. In particular, in the case of a two-body system consisting of a planet and the Sun, angular momentum is constant as long as no external forces act upon the planet. The angular momentum of a planet at any point along its orbit is defined as r times its mass m times its velocity v times sine phi. Therefore, our constant k equals L divided by 2m. So now we have several ways of expressing the same quantity. dA dt signifies that we are talking about the area swept out by a planet per unit time. K indicates that this quantity is constant for a given orbit, consistent with Kepler's second law. 1/2 times r times v times sine phi is the general expression for this quantity at any given point in the planet's orbit. 1/2 times rp times v naught is the expression for this quantity at a particular moment in the orbit, that is, when the planet is at perihelion. And L divided by 2m reminds us that we can think of k being constant as a consequence of the law of conservation of angular momentum in our Sun-planet system, where the only force in effect is the gravitational force between the two. We now consider yet another useful way of thinking about the infinitesimal change in area, dA. If the orbit were a perfect circle, R1 and R2 shown here would be equal, and the area of a section of a circle is exactly r squared times theta in radians. However, we are assuming that the orbit is not a circle, and so R1 and R2 are generally not equal. Nevertheless, we will use the area formula for a section of a circle as an approximation that becomes more and more accurate as d theta approaches 0. Imagine that for r, we are using the average of r1 and r2. I want to give you a heads up here. We are looking for an expression for dv divided by d theta. We want to remember that dv depends on the gravitational field applied during an infinitesimally short time interval. Even though dt is as arbitrarily close to 0 as we want it to be, we still want to consider the fact that the planet moves an infinitesimal distance, and therefore the gravitational field changes a little bit if r and r prime are not equal. Once again, we imagine using the average of r and r prime as a very good approximation in our equation above. Let's write the equation as dv equals gm divided by r squared times dt. We recognize that both equations are strictly true only when r is constant, but we have imagined using the same approximation for r in both cases. We are soon going to combine these equations in such a way that the variable r will drop out, so we trust that any inaccuracy will be eliminated or become negligible. If we succeed in proving Kepler's first law, we can safely assume that our approximations here were justified. Now let's reintroduce another equation from earlier. That is, dA equals k times dt. Combining these two equations, boxed in purple, we find that 1/2 times r squared times d theta equals k times dt. Rearranging, we get d theta equals 2k over r squared times dt. Now let's compare the top equation, the one in the red box, with this new equation at the bottom, the one in the blue box. We can see that if we divide the first by the second, the r squareds and the dt's will drop out. The result is dv over d theta equals gm divided by 2k. For k, let's substitute the expression we found earlier, that is, k equals 1/2 times rp times v naught. And we can write dv over d theta equals gm over rp times v naught. Let's consider the significance of this equation with regard to the planet in some arbitrary orbit. First of all, note that the quantity gm divided by r sub p times v naught is a constant for any particular orbit. We can write that dv, that is the magnitude of the dv vector, equals gm divided by rp v naught times d theta. The equation should remind you of a formula related to a circle, that is, a very small segment of the circle, ds, equals the radius times an arbitrarily small change in theta. We will come back to the significance of this revelation in a moment. But first, let's look at things on a more macroscopic level. Imagine that we turn on gravity every 45 degrees, that is, every pi over 4 radians. Then we could add in the delta v's as follows. We will draw in delta v's every 45 degrees around the orbit. Their magnitude is always the same, as defined by the right-hand side of the equation above. Their orientation, of course, is such that they always point towards the sun. This is all pretty straightforward. Notice one thing, however. We still don't actually know what the orbital path looks like. So let's remove the ovoid path. As a result, we don't know how far from the sun to position the delta v's. We only know their magnitude and their orientation for every 45-degree change in the planet's angular position. You can see that I have now drawn each delta v at an arbitrary distance from the sun. In a situation like this, when you want to explore how vectors add together, but you don't know where to place them in real space, you can move them to vector space. Let me explain. Let's take this particular delta v, circled in pink, and move it into vector space. As you will see, the whole point of vector space is to provide a convenient platform for adding multiple vectors and for visualizing their relationships. In vector space, we keep the reference direction the same. When moving velocity vectors back and forth between real space and vector space, their directions and their relative magnitudes must remain the same, although the scale in vector space may be different than the scale in real space. Delta v, or dv vectors, always point toward the sun in real space. As a result, their direction in real space and vector space is always the angular position of the planet plus 180 degrees. I have added a 0 degrees at the tail of this delta v to indicate that the planet is at an angular position of 0 degrees when this particular delta v is acting upon it. We can now go back to our real space diagram and grab each delta V in succession. And import them into vector space, where we can add each successive delta V to the previous one. At each transition from the head of one delta V to the tail of another, I have noted the angular position of the planet. Notice that this exercise, turning gravity on every 45 degrees, has led us to produce a regular octagon of delta V vectors in vector space. But in reality, gravity is continuous, and so the next step in this thought experiment is to imagine a nearly infinite number of dVs adding together one by one. What is a regular polygon with an infinite number of sides? A circle, which brings us full circle back to the microscopic version of the equation. So let's take all these dVs and draw what we will call the dV circle in vector space. Obviously, I can't draw a nearly infinite number of arrowheads, so I have just drawn enough to indicate how all the dVs are supposed to add together to form a circle. Let's imagine 1,000,000 dVs for every degree. It would look like a circle because a regular polygon with 360 million sides is going to look like a circle to our eye. Notice one more time the similarity between our formula for the dV circle and the general formula for any circle, which relates ds to r and d theta. The point I want to emphasize here is that the radius of the dV circle is effectively equal to gm divided by rp times v naught. We can also think of dV as the change in velocity for every d theta change in the planet's orbital position. For every d theta that the planet moves counterclockwise in its orbit, the corresponding dV adds on to the prior dV and rotates 1 d theta counterclockwise. So let's go back to thinking about 1,000,000 dVs for every 1 degree change in theta. Now we are set up to explore how these dVs can be combined in different ways and added to our blue velocity vectors, starting with v naught. We need to answer some questions. Where should we put v naught? Which direction should it point? Of course, it is pointing straight up in our real space diagram, so it must be pointing straight up in vector space as well. Where should we place its tip? Well, the tip must touch the dV circle at the point corresponding to the planet's angular position, i.e. 0 degrees for v naught. What magnitude should it have? Well, we haven't determined its magnitude yet. For our thought experiment, we are free to choose it as one of our initial conditions. Let's choose v naught so that its tail lies at the center of the dV circle. In other words, the magnitude of v naught equals the radius of the dV circle. Thus, v naught equals gm divided by r sub p times v naught, or v naught squared equals gm divided by rp. Now, if we start with v naught and add 45 million dVs one at a time, we get this resultant velocity vector, representing the velocity when the planet's angular position is 45 degrees. If you prefer, we could add the 45 million dVs all together first to produce this macroscopic delta V representing the cumulative change in velocity. And then add that delta V to V naught. The resultant would of course be the same as before. There is a better way to say what we have just done here. We should say that we have just added an infinite number of infinitesimally small dVs to produce a delta V. As discussed in the first video, a process such as this is essentially integral calculus in its most rudimentary form. Note that if we want to find the velocity vector when the planet has an angular position of 90 degrees, we would have to sum twice as many dVs. Wait, we already summed an infinite number of infinitesimally small dVs. How can there be twice as many dVs as an infinite number of them? The answer is that infinity is not a real number, and an infinity in one context may not have the same magnitude as an infinity in a different context. Although it requires some effort to understand the concepts underlying the construction of the dV circle, once established it becomes a very simple tool to use. We can find the planet's velocity vector for any of its angular positions along its orbit. In our current thought experiment, we have chosen to find the velocity vector at each 45-degree change in position. So we can continue very easily as follows. And we now have a set of velocity vectors corresponding to the planet's velocity at a set of 45-degree increments in angular position in real space. Note that all of the velocity vectors have the same magnitude equal to the radius of the dV circle because we chose that magnitude as one of our initial conditions. We can move each of those velocity vectors back into our real space diagram. If a planet's velocity is constant, it must always be the same distance from the Sun in accordance with Kepler's second law, which we have already proven. Therefore, the planet's orbit in this special case is a circle, which is a special case of an ellipse. Every important concept presented so far can be derived directly from Feynman's lost lecture. As we go forward, however, we diverge from his proof using only geometric constructions and follow a path involving geometry, analytic geometry, and trigonometry in order to arrive at an equation for an ellipse. Nevertheless, it is important to point out here that Feynman's dV circle will continue to prove to be indispensable to our endeavor. We now want to explore what happens when the magnitude of V naught does not equal the radius of the dV circle. To simplify things and to avoid confusion, I am going to designate the radius of the dV circle with a capital R. When we experiment in a moment with a different V naught, we want to relate it back to the V naught that we chose initially, that is, the V naught equal to the radius of the dV circle. And instead of calling that initial velocity vector V naught, we are going to call it V sub ref for V reference. This new designation will allow us to distinguish it from our new V naught. V reference squared equals gm divided by r sub p. So V reference equals the square root of the quantity gm divided by rp. So now we go back to our real space diagram and we draw in V reference as shown here. Let's picture an asteroid approaching our planet as shown here. Its velocity vector is pointed in the same direction as that of the planet, but its magnitude is considerably greater. As a result, it crashes into the planet, to which it transfers its momentum. The net result is an increase in the planet's mass and its velocity magnitude, but no change in the direction of its velocity. We continue to assume that the mass of the planet is negligible compared to the mass of the Sun, so it will continue to have no effect on our thought experiment. Although the planet was previously moving in a circular orbit, we expect that its new velocity will produce a different orbital shape. More precisely, we expect that its new increased velocity will initially take it farther away from the Sun. If we assume that it will follow some sort of periodic orbit, its distance from the Sun will eventually decrease once again, and it will return to its position here at time zero at the moment of impact. Therefore, we conclude that its position at time zero represents perihelion. Let's imagine that our new V naught is 10% greater than V reference. In other words, V naught equals 1.1 times V reference. Therefore, capital R, the radius of our new dV circle, will be gm divided by the quantity r sub p times 1.1 times V reference. Let's substitute for V reference as indicated here. And we get this equation. Let's remove our real space diagram so we have more room to do a little algebra. We can see two opportunities to simplify our expression. And we get that capital R equals the square root of gm divided by the square root of rp times 1.1. But wait a minute. The square root of gm divided by the square root of r sub p equals V reference. So let's make that substitution. And we find that our new capital R equals V reference divided by 1.1. I'm putting a red box around two key takeaways, and we're going to put those formulas back into real space. And we ask the question, what is V naught divided by R? And we can see that we're going to be able to eliminate V reference. The ratio of our new V naught to our new capital R, the radius of our dV circle, is 1.21. We can write this same relationship in each of three ways, as shown here. We can now use this relationship, V naught equals 1.21 times capital R, to start to fill in our dV circle diagram. We indicate the center of the dV circle with a point, P1. We indicate the radius of the dV circle, capital R, as shown here. We now draw in V0 in its appropriate position and with its appropriate magnitude relative to capital R. Notice that because V0 can also be written as capital R plus 0.21 capital R, the distance from point P1 to point P2 must equal 0.21 times capital R. Having set up our vector space diagram to this point, let's go back to real space. The situation when the planet is at perihelion is much as it was before, except remember that V0 now is greater than V reference by 10%. However, we suspect that the orbit is no longer a circle, and so to avoid biasing ourselves by supplying the correct answer, let's imagine once more that the orbit is now an ovoid. As before, dA divided by dt equals 1/2 times Rp times V0. Now let's place the planet at some other arbitrary position along its orbit. There is one independent variable, namely its angular position theta. There are three dependent variables. First, its distance from the Sun, r sub theta. Second, its velocity vector, v sub theta. And finally, the angle formed by r sub theta and v sub theta at the planet, namely the angle phi. We know that we have already established that in general, dA dt equals 1/2 times r sub theta times v sub theta times sine phi. Therefore, r sub theta times v sub theta times sine phi equals r sub p times V0. Recall that our goal is to arrive at a formula for an ellipse, namely r sub theta equals r sub p times the quantity 1 plus e, all divided by the quantity 1 plus e times cosine theta. We are going to use the dV circle in vector space as a tool to reach our objective. So here's what our dV circle diagram looks like so far. Now let's add in the blue velocity vector v sub theta. In accordance with the rules of vector addition, we place its tail at the point P2, and we place its head at a point on the dV circle which we will call P3. We don't know the exact location of P3 at this point, but it is determined by the angle beta shown here between V0 and v sub theta. Now we want to go back to our diagram in real space and find the relationship between beta and phi. Notice that I have drawn two dotted lines through the planet. They are perpendicular to each other. Let's call them x and y. X is parallel to r sub p, and y is parallel to V0. So here are beta and phi. We can see that the angle formed by v sub theta and y is beta because y is parallel to v naught. Meanwhile, phi we can see as the sum of two angles. The pink angle and the purple angle. Now the pink angle is equal to theta because x is parallel to RP, so we're dealing with alternate interior angles. We will call the purple angle alpha. Now there are two relationships that we want to take away from this diagram in real space. First, phi equals theta plus alpha. Second, alpha equals 90 minus beta. We're going to use these relationships in our analysis of our dV circle diagram in vector space. So let's go back to where we left off. And we draw a line segment from P1 to P3, which we label capital R, as it is the radius of our dV circle. We draw a line segment from P3 to P4. And we note that the length of that line segment is r sine theta, while noting also that the line segment from P1 to P4 has a length of r cosine theta. I want to tell you where we're headed. Our next major goal is to find an expression for sine phi. So remembering this relationship that we found, phi equals theta plus alpha, we can say that sine phi equals sine of the quantity alpha plus theta. In order to find an expression for sine phi that is useful to us, we are going to refer to our dV circle diagram, and we will also use three trigonometric identities that I will list as we go along. First, we have the sine of an angle sum. That is, sine of the quantity alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. Therefore, we can write that the sine of alpha plus theta equals sine alpha cosine theta plus cosine alpha sine theta. Next, we recall that we found that alpha equals 90 minus beta. So we write down that sine alpha equals the sine of 90 minus beta, and cosine alpha equals the cosine of 90 minus beta. The next useful pair of identities is the sine and cosine of 90 minus an angle. So the sine of 90 degrees minus alpha equals cosine alpha, and the cosine of 90 degrees minus alpha equals sine alpha. So we can write that sine alpha equals cosine beta, and cosine alpha equals sine beta. So, substituting expression 2a and 2b into expression number 1, we get sine phi equals cosine beta cosine theta plus sine beta sine theta. Now, simply by inspecting our dV circle diagram, we can find useful alternative ways of expressing cosine beta and sine beta. So, for example, we can see that cosine beta equals the quantity r cosine theta plus 0.21 r, all divided by v sub theta. We multiply that quantity by cosine theta, and we now have an alternative way of writing the first term of our expression for sine phi above. Next, we recognize that sine beta equals r sine theta over v sub theta. When we multiply that quantity by sine theta, we have a new way of writing the second term of our expression for sine phi above. Expanding the numerator of the first term and adding it to the numerator of the second term, we get r cosine squared theta plus 0.21 r cosine theta plus r sine squared theta all over v sub theta. Factoring out r and rearranging, we get r times the quantity cosine squared theta plus sine squared theta plus 0.21 r cosine theta all over v sub theta. But cosine squared theta plus sine squared theta equals 1. In accordance with the Pythagorean identity. So now we see that sine phi equals r times the quantity 1 plus 0.21 cosine theta divided by v sub theta. Now let's take this finding and bring it into our diagram in real space. So, in the red box on the left, we have an expression for sine phi, which we can plug into the equation in the red box on the right. Take a moment and see how these expressions relate to the diagram of our orbit in real space. And remember once more that our goal is to find an equation that reflects an equation for an ellipse, such as the one shown in the bottom right. We're going to need a little more room to do some algebra, so I'm going to remove this diagram of the orbit. I want to bring back one other useful expression. Here is the expression for v naught that we found earlier. So, substituting first for sine phi, we wind up with the equation in the blue box. Notice that the v sub thetas cancel out. And we are left with this equation in the blue box, and we are now ready to substitute for v naught. Let's divide both sides of this equation by capital R. Now let's just make a wild guess and suppose that E equals 0.21. Substituting then for E, we get this equation in the blue box. And all we need to do now is divide both sides by the quantity 1 plus e times cosine theta, and we get the equation for an ellipse that we have been looking for. In sum, we have proven Kepler's first law by using relationships revealed in vector space, with the dv circle as a framework, to derive an equation for an ellipse, shown here in the blue box, from the equation above in the red box. The equation in the red box, of course, we derived from Kepler's second law, and it is a corollary of the conservation of angular momentum. In addition, we have a new way of thinking about E, the eccentricity of an ellipse, by referring to the dV circle. E is simply the quantity V0 minus R divided by R. You are now ready to proceed to video 4, proving Kepler's third law.